Today we're going to continue looking for patterns, looking for ways to remember our sine, cosine, and tangent of trig functions, of angles on quadrants, 0, 90, 180, and 270, and any angles with a reference angle of 30, 45, and 60. We want to sort out what those values are, and then we'll be able to combine that with what the quadrant information. Sine is positive when y is positive. Cosine is positive when x is positive. Tangent is positive when x and y have the same sign. So remember what's positive where. Then we'll remember the values that go with 30, 45, and 60 in sine, cosine, and tangents. And then we'll know the circle all the way around. Here are the two triangles. I realized that I said around the unit circle with two triangles. Then I drew three triangles. And people are like, oh, dude, this guy teaches math and he can't even count. But you have to remember, there are only there are only three kinds of mathematicians. Those you can count and then you can't. So here are the actual two triangles that we're going to work with. In fact, this one is twice as much triangle as we need. The triangles that we're going to work with are half a square and half an equilateral triangle. So we're going to use an isosceles right triangle. And we're going to use half an equilateral triangle. An isosceles triangle just means two sides are the same length. So isosceles just means two equal sides. This also means two equal angles. Angles opposite equal sides are equal. And we're going to imagine it by taking a square and cutting it down a diagonal. So if we have a square, and let's say the sides of the square are length 1, there's our isosceles right triangle. The two legs are going to be 1, and the two angles will be 45 degrees. Because the angles opposite equal sides must be equal. And if I use 90 degrees up for my right angle, that leaves 90 degrees to be split evenly between the two other acute angles. So they're both going to be 45. Then what we want to do is figure out how long the diagonal is. Since we have two sides, we can use the Pythagorean theorem to figure out what the length of that diagonal. So I'll have 1 squared plus the other leg, other 1 squared is the square of the hypotenuse. So that tells us that the hypotenuse squared is equal to 2. So the hypotenuse is the square root of 2. Any questions? Nothing up my sleeves, just a little bit of algebra with some Pythagorean theorem. Normally, when we're solving an equation with an even exponent, we have the plus or minus. Not worrying about the minus one because we're trying to find the length of that diagonal, and it's not going to be a negative number. At this point, we might notice that the one I drew above for my 45-degree angle is supposed to fit inside a unit circle. And so I made the hypotenuse equal to 1. And so there's a problem here because I've got the hypotenuse of square root of 2 down here, and I got a hypotenuse of 1 that I have up in my triangle that I'm going to stick in my unit circle. Remember, the unit circle has a radius of 1, and the hypotenuse is always going to be sitting on the radius of the circle. So my hypotenuse is too big. It's a square root of 2. But so what we're going to do is use similar triangles. I'm going to divide the hypotenuse by by square root of 2 to make its length equal to 1. So I'm going to use similar triangles and divide all the sides by the same factor. I can multiply all the sides by the same factor. So I'm going to use similar triangles. And I'm going to make the hypotenuse equal to a length of 1 by dividing it by square root of 2. But if I do that to the hypotenuse, I have to do that to the other sides. So the square root of 2 divided by the square root of 2 is equal to 1, like we have up here. And 1 divided by the square root of 2 is just going to be a 1 divided by the square root of 2. And on this side here is going to be also a 1 divided by square root of 2. Any questions? Is everybody okay? We have to dig up some old rules. There used to be old rules where it wasn't okay to have radicals in our denominators. So we are going to rationalize our denominators. That's the process by which we get rid of radicals in the denominator. So 1 over the square root of 2 is also going to be written as, so we start off with 1 over square root of 2. And we multiply by root 2 over 2. Root 2 over root 2. In the numerator, we have 1 times the square root of 2, which is the square root of 2. In the denominator, we have square root of 2 times the square root of 2, which is the square root of 4, which is 2. So the other way to write 1 over the square root of 2 is square root of 2 divided by 2. From a practical standpoint, we don't really need to rationalize things, because if I want to know what 1 divided by the square root of 2 is, I just ask the calculator, hey, calculator, what is 1 divided by the square root of 2? And it tells me it's 0.7071. This is the same as if I take 2 and divide it by the square root of 2. I did it upside down. 1 divided by the square root of 2, 0.7071. If I take the square root of 2 and divide that by 2, I also get 0.7071. If you look at this and think, heck, I don't remember rationalizing denominators, not important. What is important is recognizing that 1 over the square root of 2 and square root of 2 over 2 are the same number. It's just different representations of the same number. So the practical thing to know right now is that 1 over root 2 is equal to square root of 2 over 2. If you want to write it sideways, like I wrote my adjacent side, 1 over square root of 2, just make sure you're careful with your radical bar. So that the radical definitely ends before we divide by 2. How's that, okay? All that just for me to tell you that if the hypotenuse is 1, the two sides are going to be root 2 over 2. That's the most common way you're going to see things like sine of 45. How's everybody okay? You sure? You don't look okay. You all look like you look very pained right now. Is it just because it's hot? It's like to do anything but like this takes too much energy, and it's too hot for that. Oh yes. So this took me a very long time just to say sine of 45 is going to be square root of 2 over 2. That's the key thing that we have to remember. Sine of 45 is root 2 over 2. Because we're going to take opposites over hypotenuse. Convenient for sine and cosine. We take opposites over hypotenuse. We do root 2 over 2 divided by 1. So we get root 2 over 2. And I'm going to write them sideways style. So I'm going to have to be careful that my radical ends before my dividing. Cosine of 45 is going to be adjacent over hypotenuse. So root 2 over 2 over 1. So just root 2 over 2. Tangent to 45 is opposite over adjacent. And since they're the same, tangent to 45 is equal to 1. That's the takeaway. TLDR, sine 45 equals root 2 over 2. Cosine 45 is root 2 over 2. Tangent of 45 is 1. Everything else is just structure to help us remember those 3 values. How's everybody okay? Michael, why didn't you just say that and move on? Michael, because that's not how this job works at all. You need to say one thing that will take 10 seconds, make sure it takes a half an hour. This is what they teach us in teacher school. I'm just kidding. I never went to teacher school. I just went to school and tried to figure the rest out from there. The other thing that we want to note is that sometimes we're going to be using our calculator, and our calculator is not going to be telling us things like root 2 over 2. So we should recognize the decimal approximation of root 2 over 2, 0.7071. So that when our calculator barks out this number, 0.70710678812, say, oh, that's our calculator telling us square root of 2 over 2. So we should know that this is approximately equal to, it's hidden if I do that. This is approximately 0.7071. That would be a handy number to carry around as well. Sine of 45 is root 2 over 2, which is approximately 0.7071. You don't have to memorize that. You do have to remember it. How's everybody okay? Yeah, Isosceles right triangle business is just to help us remember where this stuff came from, where these numbers came from. Imagine the one and the square root of 2. Cut it down in signs by dividing everything by the square root of 2. We have to remember how to rationalize our denominators because we have to pick 1 instead of making the hypotenuse equal to 1 right away. So that's one of our triangles, the isosceles right triangle. The other triangle that we want to use is half an equilateral triangle. So an equilateral triangle just means 3 sides are equal, 3 equal sides. Which means 3 equal angles. Since the sum of the angles in any triangle is 180 degrees, and here we're saying they're all going to be the same, we just take the 180 divided by 3 and come up with 60 at every corner. So it's 60, and 60. Now this one at the top is also 60, but I don't want to list it as 60 because I said we're going to be using half an equilateral triangle. So I'm going to split this one down the middle. Now, if I cut this side opposite in half, I cut the opposing angle also in half. Because I'm making a right. Actually, it doesn't matter. So I'm going to cut that top angle in half. Instead of just being one big 60-degree angle, it's going to be 2 30-degree angles. Splitting it up. And now we've got one triangle with a 30-degree angle and a 60-degree angle, which we've decided are important angles. I don't know if you've decided, but it's been decided that these are important angles. Were they important to somebody? So now they're important to you. Yeah. So everybody loved them. 30, 60 right triangle. One of our favorites. Here's what we're going to do. Because I'm cutting stuff in half, I'm going to make the side of this triangle equal to 2. First of all, this side is, I'm going to pick the left side. And I'm going to say, let's suppose that the side is equal to 2. Since it's an equilateral triangle, that means all the sides are equal to 2. And since I cut that bottom side in half, that means the part that I care about down here is a 1. So now I got to figure out the height of this triangle. So if this is side A, I have a hypotenuse of 2. This side opposite the 30-degree angle is a 1. I got to figure out the side opposite the 60-degree angle. And so we use the Pythagorean theorem again. A squared plus 1 squared is hypotenuse squared. Oops, I know what the hypotenuse is. Oh, Zoom is slow again. Lag. Equals the hypotenuse, which is 2 squared. So a plus 1 is a squared plus 1 is equal to 4. So a squared is 3. So a is the square root of 3. Are we okay? So the sides in this triangle are 1, square root of 3, and 2. Square root of 3 is a number we should recognize. So the square root of 3 is equal to 1.732. So we should recognize the square root of 3 is 1.732. Keep that one in mind. So that makes sense. I got the small side is 1. The smallest leg is 1. The middle leg is 1.732. And the long leg is a 2. So everything seems in order. But the triangle that we have up at the top, has a hypotenuse of 1. And right now, my side opposite is the square root of 3. So if I want to cut the hypotenuse down from 2 to 1, I need to divide everything by 2. So my side opposite the 60 is going to be a square root of 3 over 2. The side opposite the 30 is going to be a 1/2. And so now I can figure out my sine, cosine, and tangent of 60 degrees. And once we have that, we'll be able to put it into any quadrant because we know where sine's positive, we know where cosine is positive, we know where tangent is positive. So the sine of 60 is opposite over hypotenuse, or root 3 over 2. Cosine of 60 is adjacent over hypotenuse, or 1/2. Tangent of 60 is opposite over adjacent. Root 3 over 2 divided by 1 over 2. We can cancel out the over 2. So root 3 halves divided by 1/2. Cancel out the halves, and we just get root 3. We should know our decimal approximations of these values. Square root of 3 is approximately 1.732. We know that 1/2 is exactly equal to 0.5. And root 3 over 2, we should have an approximation of that. Let's just take our square root of 3 and divide it by 2. 0.8660. Sine of 60 is root 3 over 2. Cosine of 60 is 1/2. Tangent of 60 is root 3. We split an equilateral triangle with side length of 2 to help us remember those values. Since we have these values going around with the 60, we can just flip this around and have the same values for 30. So opposite the 30, if it's a 60 down here, that means it's a 30 up here. So opposite the 30 is a 1/2. Opposite the 60 is root 3 over 2, or adjacent to the 30 is root 3 over 2. So now we know that sine of 30 is 1/2. Cosine of 30 is root 3 over 2. And tangent of 30 is 1/2 over root 3. The halves still cancel. We end up with 1 over the square root of 3. This is not the most common way we'll see this fraction. We should rationalize this as well. So 1 over the square root of 3. It works the same way as we did with 1 over the square root of 2. This is equal to root 3 over 3. We should recognize the decimal equivalent in case we need to check something on our calculating machine. So we'll do root 3 over 3, and that is approximately 0.5774. Now we know sine, cosine, and tangent of 30, 45, and 60. We'll take our knowledge of quadrants to move all those into figure out references. Question? Is everybody okay? One of the questions that should come up is, why do we have to remember these values? Don't we have calculating machines? Remembering the values isn't actually the point. Looking for patterns and recognizing patterns and using that to help us remember these things that aren't actually important to us. That is the point. Finding a way to remember these values by looking for the structure, that's the point. We get at this point by making you remember these values without just memorizing. Otherwise, we could have been done with this like 30 minutes ago. Somebody call, see these 9 values, learn them. Go. Like I said, 30 minutes of information packed into 3 hours. That's how school generally goes. To borrow a description of D&D. 30 minutes of fun packed into 3 hours. Is everybody okay? Are you sure? I think some of you are lying. That's okay. That's the dynamic. It's like the teacher-student thing. Students just naturally lying to their teachers. It's a normal part of the bargain. You know what I mean? And it's like some of you might become teachers. I don't know if that's in your plan. Some of you might become teachers anyway. I don't know. But one of the things you need to recognize, one of the things you need to get over is being mad when people are lying to you. This is going to be a regular thing. You're going to get an email from a student and say, oh man, I can't come to class today. I'm sick. No one wants to use that these days because of like COVID and shit like that. So I'm going, no, it's not COVID. It's something else. It's just a cold. But you're going to get those kind of emails. Students go, oh, I can't come in because I'm sick. I'm like, oh no. Make sure you get lots of rest and get well soon. And I go, ha, he doesn't know that I'm not actually sick. I just wanted the day off. I'm not sick. I'm just sick and tired of math. But really, I do know. Every time you lie to me, I know when you're lying to me. It's just that sometimes it's okay. Do you know what I mean? Some teachers are like, I think they're lying to me. Bring me a doctor's note. Well, what are we, children? Prove it. Prove that you're sick. You become teachers, don't do that. Especially if you become a teacher at this level, where you're dealing with adults. I don't know if y'all think of yourself as adults, but I think of you all as adults. And so if you tell me you're sick, I'm just gonna fucking believe it. Because it's ridiculous. Like, I'll bring me a note, prove that you were sick. What if you're not sick enough to go to the doctor, but you have enough respect for your fellow students that you don't want to infect all of them because you think you might be sick? You know what I mean? You go to work when you're sick and infect everybody else. Prove how tough you are. Well, defense stipulates that you're a tough guy, boomer. Why don't we just stay home? I know I hack on old people a lot, but that's only because they're annoying. So has everybody got these 9 values memorized? Because we got to take them all the way around the circle, all the way around. Fortunately, they aren't going to change because I'm going to be using these references. Seems like a lot to remember, but that's only because it's a lot to remember. And you have to remember all of it. All the time. In perfect detail. All right. So we know our values. Sine of 30 is a half. Cosine of 30 is root 3 over 2. Tangent of 30 is root 3 over 3. We also know that cosine is the x coordinate, sine is the y coordinate. So let's go around and we also know what all of our angles look like, all of our reference angles look like in each of the quadrants. So here I've marked them out and color coded them. The red ones are all 30s, the green ones are 45s, and the blue ones are 60s. So here's our 30-degree reference angle. So we know that the sine of 30 is a half. The cosine of 30 is root 3 over 2. And that root 3 over 2 and 1/2 are also the coordinates of that point on the unit circle. This is the reason that I want us also to remember the decimal approximations of these numbers so we can see that this makes sense. This one is more x than it is y. And root 3 over 2 is 0.866, whereas 1/2 is 0.5. So that tracks. There's more x than there is y. Next up in the first quadrant is our 45. Here's a 45-degree angle. We know that cosine of 45 is root 2 over 2. And sine of 45 also root 2 over 2. That makes sense. We're on a 45-degree angle. The slope is 1. The equation of that line is y equals x. That's the equation of a line with a slope of 1 through the origin. Y equals x. And that's what we've got here at this point. The y and the x are the same value. We also note that there's a little bit less than cosine 30, but a little bit more than sine of 30, and that tracks. Root 2 over 2 is 0.7071, which is more than a half, but less than 0.8660. Everything is matching up so far. Here we are at 60 degrees. $60 and $30 are complementary. They both sit inside the same triangle. So the opposite of one of them is the adjacent of the other. So it makes sense that the cosine and sine just switch places when we go from 30 to 60. Cosine of 60 is a half, sine of 60 is root 3 over 2. Looking at that point on the unit circle, that tracks, because that point is higher than it is far away. It's a half on the x and 0.8660 on the right, so that is the right location for that point. Everybody okay? Good. It only seems like a lot to remember because it's a lot to remember. Now I want to keep going at this pace, and then we'll do it again right afterwards. I'm just kidding. I can only handle doing this once a day. Actually, I can't even handle doing this once a day. As a teacher, I can only handle doing this half a time a day. And then I force you to do the rest of it. That's like dirty teacher tricks 101. If there's a problem that you don't want to do, just assign it. Make it a quiz. If you're worried about how people will feel if you call something a quiz, don't call it a quiz. Just say it's classwork or homework. Students like homework, especially if there's not like a thing that you're going to have to turn in. Like if a teacher says, read section 1.3 for homework. In math class, that translates in student language to no math homework. Let's go into the second quadrant. That 60-degree angle in the second quadrant, it's 60 degrees from this terminal side down to the nearest part of the x-axis. So that means it's 120 degrees. That's our 60-degree reference angle. That's our 60-degree reference angle in quadrant 2. Note that in quadrant 2, the y coordinates are going to be positive, the x coordinates are going to be negative, which means sine is going to be positive and cosine is going to be negative. So over here, we'll have cosine of 120 is negative 1/2, and sine of 120 is positive root 3 over 2. Makes sense. We're in quadrant 2. The x is negative. To get from the origin up to this point, I have to go negative in the x, then positive in the y. Negative cosine, positive sine. It's like I hooked up a delay pedal in the camera. Bam, bam. It only does one. "45-degree reference angle in quadrant 2 corresponds to 135 degrees in standard position. So our values are going to be root 2 over 2 and root 2 over 2, but the cosine will be negative because we're in quadrant 2. So cosine of 135 is negative root 2 over 2, and sine of 135 is positive root 2 over 2. And then finally, we get to a 150-degree angle because it's 30 degrees from the terminal side of 150 to the negative x-axis. Since it's a 30-degree reference angle, cosine is going to be root 3 over 2, but negative because we're in quadrant 2. Sine is going to be 1/2 and positive since we're in quadrant 2. So cosine of 150 is negative root 3 over 2. Sine of 150 is 1/2. Combination of those two triangles and knowing what's positive where. The other thing that we would want to note is what's going on the quadrant angles. So here's a 0-degree angle. Since we're on the unit circle, the coordinates of this point are 1, 0. And so that tells us that the cosine of 0 is equal to the x-coordinate, which is 1. And the sine of 0 is the y-coordinate, which is going to be 0. Now, if we go up to the positive y-axis, where we're at 90 degrees, the coordinates of this point are 0, 1. So that means the cosine of 90 is the x-coordinate, which is 0. So cosine of 90 is 0, and sine of 90 is 1. I want to finish out a half cycle. So if we keep going to the next quadrant angle, that'll be at 180 degrees. And the coordinates of this point will be -1, 0. So the cosine of 180 is -1. And the sine of 180 is back to 0. So now if we track the sine going from 0 to 180, just halfway around the circle, we can see that the sine values start off at 0, and then the sine increases up to 1, and then decreases back down to 0. So 0, then 0.5, 0.7071, 0.8660, 1, 0.8660, 0.7071, 0.5, 0. So it started off at 0, it went up to 1, and then back down to 0. Cosine started off at 1, and if we just think about the x going around the circle, it starts off at 1, goes down to -1, and then comes back up to 1. So cosine of 0 is 1, then 0.8660, then 7071, then 0.5, down to 0, down to -0.5, -0.7, -0.86, -1. So we can see the cosine starting off at 1, going down to 0, and then down to -1. And then we can see going, if we continue around, -1, back up to 0 at 270, back up to 1 at 360. Any questions? Okay. So the next thing that we want to do is we want to take the angle theta, and instead of having it go around a circle like this, I want to take theta and I want to put it on the horizontal axis. And I want to make a function that goes up and then down and then up and then down. We need to know what's going on when theta goes from 0 to 360, because after that, it's the same thing again. I go from 0 to 360, and 360 to 720 looks like a copy of 0 to 360, because we're stuck on this circle. Let's take 5, come back and stretch out sine or cosine.